All right, let's look at this discussion problem. This is trying to investigate a yo-yo. So we have a yo-yo. We say that it has a mass m and an outer radius r. And so let's kind of start drawing our picture. So here's our yo-yo. And it's got some radius r and a mass m. This looks more like an r. The central stem has negligible mass, and so that's like a little tiny piece here, and radius little r. So maybe I'll make it a little bit bigger. And so this is the part that the rope is wrapped around. And so this one here, again, it's got a little radius r, and this is where the rope is acting here. So that's sort of our model of a yo-yo. So again, it's got mass m, outer radius big R, and then the central stem, which we're going to say is basically massless, and it has radius r. And the string of negligible mass is wrapped around it. The string is held taut and held vertically, and the yo-yo is released from rest. So we're just letting it go from rest. The question is, how long does it take for the yo-yo to hit the ground, which is the distance h below the initial position? So what we're going to do here is approach this in a way that we have been doing all quarter. We're going to look at this object and do its free body diagram, and then using a couple Newton's second law equations, we're going to try to figure out the acceleration of the center of mass of this yo-yo, and then use kinematics to see how long it takes to go down at distance h. And so let's look here. Here's our yo-yo. Our free body diagram would look like this. There's basically two forces. The tension going up and the mg going down. So we're going to look at this, and we'll do two. So the first thing we'll do is we'll look at this as just F equals ma style equation. And so I'll call this positive y going upwards. And so I'll say the sum of the forces in the y direction are going to be equal m times the acceleration, and this would be the acceleration of the center of mass of the yo-yo. And so let's look at our forces. Well, there's a positive tension, a negative mg, and we can say negative ma, because we know the acceleration of the yo-yo center of mass will be down. And so we have this equation, but again we have two unknowns. We have the tension and the acceleration. So the next equation that we'll use, because this object is also rotating, is I'll look at the sum of the torques equals the moment of inertia times alpha. And so what I'm going to do is I'm going to look at this, and I'm going to use the axis of rotation to be the center of the yo-yo right here. And so in this case, the sum of the torques, well, the torque that's going to be making this rotate would be due to the tension. And this is actually kind of our classic case of a torque. So the tension is coming off here. Oh, and so if you look at our moment arm, it's just going to be this distance right here, which is going to be this little tiny r, right? And so this is the case where, again, the tension's coming off tangentially from this central stem, and so the torque caused by that will be the tension times the r of the central stem. And that's going to equal the moment of inertia of this disk, which we're just modeling this. In this case, it's just going to be 1/2 m big R squared, right? And so we're told that this is sort of like a cylinder, and then we're also told that this central stem, we're going to basically neglect its mass. So you can't get more complicated, but this is just a little bit of a simplified version. And then here is my alpha. And so again, we got two equations. So now we have three unknowns. We got the tension, the acceleration, and the alpha. Well, how am I going to connect those two? Well, I'm going to connect those two by looking here at the tension. And so if you look at this here, this yo-yo is essentially, you can view it as kind of rolling without slipping from this point right here. And so what we can do is we can relate the acceleration of the center of mass, which again is this acceleration over here, with the angular acceleration, again, times that little tiny r. And so basically the acceleration of the center of mass we can relate very much the way they did rolling without slipping to the angular acceleration this way here. And so we can take this and say angular acceleration equals acceleration of center of mass over that r, and put it in here. And so all together, this other side will be 1/2 m capital R squared. Again, the inertia is the whole of the yo-yo, and so it's the big R. And then this alpha is basically, again, that the center is sort of rotating off of this point right here, and so it's sort of rolling without slipping off of the central stem, which has a radius of r. And so then for alpha over here, I write ACM over r. And so that's, and then so let's do what we usually do and work to sort of combine these equations. So I got, again, TR equals 1/2 m big R squared. I'm just going to call this acceleration now, just because to make it a little bit nicer to look at, and an R. And so what I'm going to do is divide both sides by an R, and so I get that the tension, one way to express it is 1/2 m, and I'm just going to write this as big R over little r squared times A, because when I divide it by the little r, I get another factor down there. And what I'm going to do now is go over here and basically plug these two equations into each other. Okay, so here we are. Here's this new version of tension. And so I'm just going to plug this in for the T. And so I'll get something like this. 1/2 m big R over little r squared A minus mg equals minus ma. And so, again, this is the kind of thing that now we want to do is we want to isolate the acceleration terms with acceleration on one side, and then the other guy on the other side. So if I do this, I'll get 1/2 m r over r squared A, and then I'll add that ma term to both sides. And then on this side over here, I've got now the mg. So let's just stop for a second. I've got an m in every piece, so let's just get rid of that. That makes this a little bit easier to visualize, and so then I got this A 1/2 m plus m. Oh, excuse me, we just got rid of the m's. Beg pardon. So I'll pull out the A, and I get 1/2 this r, big R over little r squared piece. Big R over little r squared plus 1 equals mg. And again, so we often write it kind of this way. And so then this, hopefully, you can see it kind of has the flavor of, the force that's kind of accelerating this guy here is this mg. And then, and I guess we get rid of that m again. Okay, and so yeah, and so this g will have the same units as acceleration, and this guy in here is going to be unitless because of these r's. And so we can go through and solve for our acceleration. So our acceleration will be g, all divided by, and I'll just go ahead and flip these two, make the 1 first, because it's a little bit nicer that way. So 1 plus 1/2 r over r squared. So that's our acceleration. And so let's just think about this for a little bit. If I just dropped the yo-yo, the acceleration would be g, right? And so if you look here, what happens is this acceleration, you're taking g and you're dividing by something. Now we don't know what this is because we don't know what the r's are, but this is going to end up being something bigger than 1 because I'm adding a term to 1. And so this acceleration that we have here, so the acceleration right here, this acceleration is going to be less than g, which is what we expect, right? We expect this yo-yo to not have the same acceleration as dropping or to be going faster, right? So that's our acceleration, and now it's basically a kinematics problem. And so how long does it take the yo-yo to hit the ground? And so we pull out this equation from the first couple of weeks of class, this guy here. So we'll go like this, and of course let's call this a negative, so we'll call that negative just because I know that if I call this positive y, that's going to be going upwards. And so what I'll do is I'll call my initial position 0, my final position negative h, right? So we go back to our picture here, where basically, this thing's going to drop some height h, and I'm going to again call this to be height y of 0, so this will be negative h when I hit that bottom. We're told that this thing goes, starts from rest, and so it'll be negative 1/2, and then this acceleration is this really nasty thing here, g over 1 plus 1/2 r over r squared times t squared. So the negatives will cancel, and then let's see, when I'm all said and done here, I'll get 2h divided by g, which again, the 2 comes from here, and the g comes from here. and then it'll be multiplied by this ugly term here, like that, and then all of this square rooted. And so this is our answer. Again, we can kind of look at this. So I'll separate two different pieces. I'll do square root 2h over g, and then I'll have another square root. I can always do this, is of just that more complicated piece here, 1/2 r squared over r squared. And so you can see that basically this term here, again, we don't know what this is, but this is going to be bigger than 1. And so if we just drop the yo-yo, the time would have been radical 2h over g. But in this case here, we've got this other term that's going to be something bigger than 1, so thus increasing the time, which again is what we expect here, right? So it's always good at the end to kind of check and make sure that what you get kind of makes sense with what you're expecting. All right, thanks. I hope this helps.